Another example for finding inverse functions is this one. So considering the function here, so we have, you see, a parabola. Okay, so the function is a parabola, so therefore you should have the understanding here that a parabola is going to look like this. Now, so if this function was just the parabola, would it have an inverse? Well, it is a function if we do a vertical line test. However, if we do the horizontal line test, you'll see that it's not a one-to-one function. Therefore, this parabola wouldn't have an inverse function. So, what we then do is we can restrict what the domain is going to be. You'll see what we have here is we have a restricted domain. So what we're going to do by doing this is we restrict the domain to make it a one-to-one function. So when we have this parabola, if we didn't restrict the domain, it wouldn't have a one-to-one. It wouldn't be one-to-one, so it wouldn't have an inverse function. But we can restrict the domain, therefore it will be a one-to-one function, therefore it will have an inverse function. So what I want to do here is I'm just going to look at sketching this. So if we've got y equals x squared plus 2x minus 1, I want to sketch this function. So what I want to do is I want to see what the turning point is going to be here. So we've got y equals x squared plus 2x. So what I'm going to do is half the coefficient of x. So the coefficient of x is plus 2. I half that goes to 1. I square it. And then I add it on. I don't want to change the function in any way, so if I add 1 here and I take away 1 here, then effectively I'm not doing anything to the function. And then this negative 1 is this negative 1 here. Okay, so writing this in turning point form, this is going to be x plus 1, okay, because it's always x and then what half the coefficient of x was, which was plus 1. And then we've got minus 2. So what we have here is we have a parabola with a turning point of minus 1, minus 2. So this parabola, you see, is going to have a turning point minus 1, minus 2. It is a minimum one. So then it's like this. So this is me drawing the parabola without any restrictions, so just ignoring this bit at the moment. So what the question's asking us for is, what's the largest value of a for which the inverse function to exist? So basically for the inverse function to exist, it needs to be a one-to-one function. And you can clearly see from the graph here that it's not a one-to-one function. So what we can do is we can make these one-to-one functions. So basically, if you think about this, if I just restricted the domain just to have anything here in this yellow section here, you see? That yellow section there would be a one-to-one function. Alternatively, if I just restricted the domain so that I just had this green section here, the green section of the parabola therefore would also be a one-to-one function. So you can form two one-to-one functions. So I could either restrict the domain so that it's negative infinity to negative 1. That would be this yellow section here, you see. Or the green section, I could have it as negative 1 to infinity. And then I would have a function like this, you see. Alright, so that would be the yellow section here. Or I would have the right hand side of the parabola. So both of these, you see, would be one-to-one functions, therefore they would have an inverse. So what this question's asking you here, you see, is what's the largest value of a for it to have an inverse? So the clue here is we're starting off at negative infinity here. So if we're starting off at negative infinity, in this question we're talking about the yellow section here. So if we're going from negative infinity, the largest value that could make this a one-to-one function would be negative 1. Anything bigger than negative 1, you see, if you came up here and you cut it to 0, that wouldn't be a one-to-one function. Okay, because then you would have this part here and I could put a line through that there, you see, and it wouldn't be a one-to-one. So the largest a value that you could have here would be -1. Okay, and that would cause our function to be 1-to-1, because then we're actually only this part of the function exists. Now the reason it says largest and doesn't just say find the value of a is if it didn't say largest, well, you could say the answer would be -2, -5, -10. Anything lower than -1 would still be restricting it to a 1-to-1 function. So in this case here, when we've got this parabola, what we're going to do is we're just drawing this part of the parabola, you see. So it's coming down here, and we're coming to here, -1, -2. All right. So this, in fact, is what the function's going to be here. So this is what f would be. Okay. All right, so the answer to the first one would be a equals -1. That would be your largest value to create a 1-to-1 function here. All right, so I've got my function now. This is going to be the domain. So let's think about what the domain and the range is. Okay, so we've got our function here. We call it f. Okay, so what's the domain of f going to be? Well, the domain of f is going to be -infinity up to -1 including. We have done a sketch here, so if we think about what the range of this function is going to be, the range is going to be the first y value we hit is -2, the last one we hit is infinity. So the range is going to be -2 to infinity. I will just correct this bracket there. Okay, I think my battery's running out. So, alright, so if we have the inverse, so without doing any calculations about the inverse, then we should be able to know that the domain of the inverse function is going to take the values of the range. So it's going to be -2 to infinity. The range of the inverse is going to take the values of the domain of the original function, which will be -infinity to -1. Alright? And this will become apparent why this is more critical now that you do this when we're doing these functions. Now, so we have a quadratic function here, so the inverse function of squaring is going to be a square root. Okay, so it's going to be a square root function. So what we're going to do is we're going to find out the inverse. Now, if we try and find out what the inverse is using the original one, you see, then we're going to have x equals y squared plus 2y minus 1. So what you're going to have in this case is you're going to have two y values, which that's going to be impossible to make y the subject then. So if it appears more than once, so when you swap the x and the y, if you've got more than one y in that function, then it's probably going to be a good idea for you to change the form. I mean, not always, but in this case, certainly for quadratics, you always have to change the form. So instead of using the original function here, what we're going to do is we're going to use it where we had it in turning point form. So we're going to use the x plus 1 squared minus 2. Okay, so we're going to write down y equals x plus 1 squared minus 2. So now you see when we swap, when we interchange the x and the y, we will be able to make y the subject because we've only got one y in here. Okay, whereas if we use the original here, you see, it would be x equals y squared plus 2y minus 1. So then you would add 1 to both sides, you see. So how would you make y the subject? It would be impossible. So in this case, you always have to put it into turning point form so that you've only got one y in your equation to solve. Alright, so next step here, we've got y plus 1 squared. What I want to do is add 2 to both sides. So this is going to be x plus 2. In this case here, we want to get rid of the squared, so think about what's the opposite operation of squaring. Well, square root, and when it's an even power, you've got to ensure that you always put in plus or minus. Okay, so we've got plus or minus the square root of x plus 2. Then what we want to do is we want to get rid of the plus 1 here. So we take away 1 from both sides and we end up with a little bit of a problem here because we're trying to find out the inverse function. What we've got at the moment is we've got inverse functions. We have 2 functions here. Okay, so what we need to look at, this is why it's a good idea to have your table here. So what we look at here, you see, is you look at the range. So this is what the range is of our inverse function. Okay, so the range is going from negative infinity to negative 1. Now if we think about this function here, how do we get values between negative infinity and negative 1? Would you do negative 1 plus values here? Now these values are all going to be either 0 or positive values when you take the square root. So do you do minus 1 plus certain values? Or would you do minus 1 minus these values? So because our range here, you see, our range is going between negative infinity and negative 1, then this is the only way that we can get values between negative infinity and negative 1. This would not work, okay, because this wouldn't give us values within our range. So therefore, we can eliminate this answer here. Alright, and then our inverse function, if we write this down nicely, is we can write f of minus 1. We're going to write down what the domain is. So the domain we know is negative 2 to infinity, which maps into our range lies within there. And then our inverse function is going to be minus 1 minus the square root of x plus 1. Alright, again, you can just check that all makes sense. Think about what your endpoint is of this square root function. So the endpoint is minus 2 minus 1. And if we look back in what we had in the graph here, the turning point of the parabola was minus 1 minus 2. So therefore, that makes sense.